Hey guys, this is Professor Denton here. I'm in Tallahassee, Florida, Generations Church, and I'm not able to be on campus Monday. We've been in and out of the hospital with my mother-in-law. Still not doing well, just to be honest with you. So we appreciate your prayers and support. I'm here at Generations Church, my old JVQ room, where I used to teach. Talked to Kayla Nugent and Kelsey Nugent this morning. They're the pastor's daughters, and they were like so excited, like, "Oh my gosh, you got one of our best friends in your interview!" Just how girls get and all that stuff. But they send their wishes to all their Kentucky friends that go down to Southeast. And so I told them that I had one of their friends in my class, and so they just thought it was the coolest thing. So anyway, a little shout out to you there. Section 11.5. I'm actually going to do a couple examples, try to keep it light and fresh like I normally do. I don't know how long this video is. We're going to do it in one take. And if I mess up, I mess up, and I'll figure it out. We'll fix it later. But I just want to go over a couple things. I actually emailed out the notes a couple weeks ago for the entire chapter 11. I will be doing 11.5. Not a ton of new stuff in 11.5. It's just kind of a pattern that we notice. We're still doing some factoring the normal way. Okay, so if you have these notes, you can print these notes off and follow along with me. It says here, don't forget to factor out a GCF if necessary. So factor out a GCF if necessary. So some of these might have a GCF, some of these might not. Here is example number 1. X squared plus 16x plus 64. Now, here's how we factored the old way. The old way was 64. We've got 1 and 64. We've got 2 and 32. We've got 4 and 16. We've got 8 times 8. And then we look and see which combination is going to factor to, it multiplies to give us 64, but it adds to give us 16. Now, as you can see, 8 and 8 would be our result. So this actually factors as 8 plus 8 times 8 plus 8. This is all review. We've factored like this before. Nothing new here in our factoring. Because these are the same, what we notice is that you can write this as x plus 8 parentheses squared, and this can be our final result. This here, this trinomial equals this binomial squared. Okay, it's just a way to rewrite. We've talked about that. Factoring is just a way to rewrite numbers. 64 is rewritten here as 4 times 16. So factoring is just simply rewriting things. So that's example A. Example B, x squared minus 14x plus 49. Okay, so we take a look at this one. We list out what are the numbers that multiply to give us 49. We've got 1 times 49. We've got 7 times 7. I believe that's all the factors we have for 49. So what result is going to give us negative 14? Well, negative 7 times negative 7 produces positive 49, but negative 7 plus negative 7 produces negative 14. So that gives us x minus 7 times x minus 7, which we can rewrite as x minus 7 squared. So you might be thinking already after 2 examples, all right, why are we doing this? If this is all review and this is all new, what's so special about this particular lesson? What's special is that we can recognize some of the patterns. If you notice that this number is a perfect square, and the coefficient here, which in this case is 1, is also a perfect square, there could be a pattern to recognize whether or not this is called a perfect square trinomial. Good thing about a video is you can pause and rewind as much as you need to. So a perfect square trinomial. If we notice that, then we can just simply jump from here all the way down to this answer here. So look, we've got 64. Mentally, take the square root of 64, which we know is 8. If the middle term is 2 times that number, this is a perfect square trinomial, which we see. Square root of 64 is 8. 8 times 2 is 16. We know it's a perfect square trinomial. Over here, what's the square root of 49? The square root of 49 is 7. Is the middle term 2 times that 7? We see there's a 14. With a minus sign here, that's going to dictate our negative signs in the parentheses. So some of the old factoring rules still apply. Where we have a plus here and a plus there produces plus, and we have a minus plus here produces a minus or subtraction sign. So the square root of 49 is 7. 2 times 7 is 14. We're checking that to see if it is indeed a perfect square trinomial. If it is, then we just simply write the factor x minus 7 parentheses squared. Okay, so that's 2 examples. Now our next example has a GCF. So we'll have to factor that out. And then I want to see if you recognize the perfect square trinomial. Okay? So again, pause, rewind, whatever you need to do to go back and look at some of the old examples. Okay? Now, question number C. We've got 2x squared minus 40x plus 200. Now, if necessary, factor out a GCF. This is in class where I would say, does anyone recognize the GCF? And like, oh, no. And we look through and we see that all the numbers are even. So the very first thing is, this is the very first day we talked about factoring, is we factor out the GCF. We divide out a 2 from every term. So 2x squared minus 20x plus 100. So we factor out the 2. Now, does anyone recognize the pattern that we just discussed a minute ago? This is a perfect square. 1 in front of the x is a perfect square. The square root of 100 is 10. 2 times 10 matches that 20. So what that tells us is that this is a perfect, oh, I messed up perfect. See, I told you I messed up. Perfect square trinomial. So we can actually jump all the way down to the final answer if we recognize that pattern. Now, if you don't recognize that pattern, just go ahead and factor the old way. 100, we got 1 and 100, 2 and 50, 4 and 25, 5 times 5, or excuse me, 5 times 20, and then we've got 10 times 10, and then we'll pick our correct combination. But here, if we recognize that, we jump all the way down to 2 parentheses, x minus 10, close parentheses, squared. What that does is that will rewrite this term, or this trinomial, in its factored form. Okay? So this is the actual answer for this factored trinomial. Now, to check your answer, which I won't go through all these, but if I wanted to check over my answer, I'll have 2 times x minus 10 times x minus 10, because that's what it means to square something, multiply it by itself twice. Then I will temporarily ignore the 2. I'll FOIL and get 2 parentheses x squared minus 10x minus 10x plus 100. So 2 parentheses x squared, combined like terms, there's where your negative 20 comes from, plus 100. Okay, and this is kind of where I was at on this step. So that's why the perfect trinomial factor pattern works, is because you see, you're going to get the same number here. That's why it's 2 times that number in the original question, because you're always going to add that number to itself, which is the same thing as 2 times the number. Okay, so that's why this is a perfect square trinomial. Okay, so that's examples A, B, and C. I've got some more examples here. I'll do a couple more, and then we'll kind of move forward with one more type. Again, you can pause, rewind. If you say, oh my gosh, he erased the board, I wasn't ready. Ah! You can always pause, rewind, and go back if you need to. So I'm going to try to keep a decent pace here. Example number D. Example D is x cubed plus 24x squared plus 144x. Again, first rule. Factor out the GCF if there is a GCF that can be factored. So we take out the x here. That gives us x squared plus 24x plus 144. Every term had an x. We factored it out. Does anyone see the perfect square trinomial pattern? 144. The square root of 144 is 12. Does this number match 2 times that 12? If it does, my final answer can be written as x times x plus 12 parentheses squared. So this x matches that x. This x plus 12 squared is what this would be if I FOILed it back out. So again, we're rewriting the term in its factored form. So far, you can always go back to the old way. 1 times 144, 2 times 72, 3 times, oh gosh, see, 42, 3 times 42, I might get a number crunch on that one. That's not right. 42 is not right. Let's see, 4, 3 goes to 4, 4 times, 48, excuse me, 48. Okay, 3 times 48. 4 times, I believe, 36, and go on down the list. But man, I gotta tell you, this is a lot faster if it follows that pattern. Okay, perfect square trinomial. Example number E, letter E. Okay, pause, rewind if you need it. Example E, 9a squared plus 24ab plus 16b squared. Now this one's a little bit different. There is no GCF. Okay, 9 and 24 have a 3, but 16 does not. 4 is the GCF of 24 and 16, but 4 is not a GCF for 9. So there is no GCF. Does this one follow the same pattern? Now, earlier, Mr. Denton, you were mentioning if you square root that number and double it, well, the square root of 16 is 4, but you double it and you get 8. It doesn't match right here. But notice here, this is not a coefficient of 1. So in the earlier example, when we have x squared plus 24x plus 144, we never talk about it because we never do it, but we probably should talk about it. What's really happening is 2 times the square root of this number, which is 1, times the square root of this number, which is 12. That's where that 24 comes from, but we never think of it that way because this is a 1. But what happens if this is not a 1? So everybody see what we've got here. So now, is this a perfect square trinomial? Here's how you find out. Square root this number, 2 times, what's the square root of the front and the back numbers? Square root of 9 is 3. Square root of 16 is 4. What's 2 times 3 times 4? 24. If that occurs, that's a perfect square trinomial. So this will factor as, notice your signs, plus and plus. This will factor as 3a plus 4b times 3a plus 4b. But because those are the exact same, we can do 3a plus 4b parentheses squared. This is the factored form of this trinomial in blue. Now, if I wanted to check my answer to see if that is right, I would FOIL this back out. So watch what happens when I FOIL this out. 3a times 3a, 9a squared. 3a times 4b, 12ab. 4b times 3a, there's that other 12ab. That's why it's 2 times, because you're adding the same thing twice. 4b plus, or times 4b is, I told you I'd mess up, 16b squared. Combine your like terms, you've got 9a squared plus 24ab plus 16b squared. Does that match the blue? It matches the blue. So that is the first half here. I'm going to check my time, make sure I'm in good shape as you guys let that sink in. 13 minutes. All right, we'll do the next part hopefully in 13 minutes or less, and we'll keep this relatively short for you today. Okay, pause, rewind, stop. If you have questions about any of this, feel free to ask questions either via email or meet me in class Wednesday. Don't come to class Wednesday and be like, I'm totally lost, I don't get anything. No, you got to come to class Wednesday and say specific questions. Can you help me with page such and such, number such and such? Hey, Mr. Jen, take a look at this question on my math lab. Can you help me with this one question? When you were doing the video, that one example, example D, example B, C, E, A, that's the one I need you to go back. Can you do that real quick? And that's what I'll try to do for you guys here, okay? All right, if you flip over to the back of that page, we have what's called the difference of squares. It's another pattern. You can factor the old way, but if you remember these patterns, you'll be able to go a whole lot faster, okay? So example at the top. We'll take a look at the top here. It says, let's consider the motivation behind when we FOIL. Now watch what happens when I FOIL this expression. We're on the back page here. I would encourage you, at least for this time, to print these notes since we're doing a video lesson. But we've got x plus 3 and x minus 3. Now, if I said, I want you to FOIL this and tell me what happens, describe to me what happens. This is what's going on. X times x is x squared. X times negative 3 is negative 3x. Positive 3 times x is 3x. Positive 3 times negative 3 is negative 9. Combine like terms. Watch what happens here. Negative 3x plus 3x goes to 0. So this becomes x squared minus 9. This is what's called the difference of two squares. Not squares the shape square with four sides. We're talking about exponents squared. The difference of two squares. See, a subtraction sign is the difference. 5 minus 3, the difference between the two numbers. Okay, the difference of two squares. Now, what we're doing on the back page of this notice is we're taking this and we're going back to this. Here's the biggest mistake students make when they're factoring the difference of two squares. If I said, hey, example, I want you to factor x squared minus 9. You know what a lot of students would do? Oh yeah, that's that difference of square thing. Oh yeah, it's x minus 3 and it's x minus 3. What's wrong with that? Something's wrong here. If you FOILed that, you'd get negative 3x, and you'd get negative 6x. But wait a second, there's no negative 6x. That's not right. The key for the difference of squares is just a pattern. Notice that the signs here were different, positive and negative. That's what's going to knock out that middle term. That's why the middle term's not there. So if you have a difference of two squares, it's going to be the square root of each of these terms. We talked about square root a minute ago. Square root of x squared is x. Square root of 9 is 3 plus minus. That's the difference of squares. Let's take a look at a few examples. Don't want to jump too fast here. Pause, rewind, all that kind of stuff. Just don't mute me. See, I told you I'd try to keep it light and fresh as best I can. Okay? You probably have already muted me. But if you've muted me, you have no idea that I'm telling you right now not to mute me. But so don't mute me. But anyway, take a look at example A. Y squared minus 4. Is this the difference of two squares? Difference, square, square. So this result will be y minus 2 times y plus 2. And that's it. Any questions? Example B. X squared minus 36. Is this the difference of two squares? Difference, square, perfect square. Remember your perfect squares? 1, 4, 9, 16, 25, 36, 49, 64, 81, 121, 100, 144, 169, 196, 225, 256, 289, 324, 361, 400, 441, 484. What a perfect square is pretty much any number times itself. 9 is a perfect square. 16 is a perfect square. 49 is a perfect square. These are all perfect squares. They're on the top of the notes that I showed you here. Those are the perfect squares. Okay? So this would become x minus 6, x plus 6. That's the factor form with the difference of two squares. But you know what? You can actually still factor the old way if you want to. I don't even know if we've done anything brand new in the last couple of days because all of this can be factored the old way. Watch here. 36. 1 times 36, 2 times 18, 3 times 12, 4 times 9, 6 times 6. 0x in the middle. So can you tell me a combination here of numbers that will subtract to give you 0? 1 and 36? No. 2 and 18? No. 3 and 12? No. 4 and 9? No. What about 6 and 6? 6 minus 6 is 0. Those are your two numbers. Those are your two numbers. But when you factor this, the only way to get 0 is to have one positive and one negative. So this is going to factor as x plus 6 and x minus 6. But we already figured that out based on the pattern, the difference of two squares. Okay? So that's really the key example here to tie all this together. I've got just a couple more. We're going to wrap this up here in just a few moments. Pause, rewind, forward, just don't mute. C, p squared minus q squared. Is this the difference of two squares? Difference, square, square. So you're going to have p plus q and p minus q. Now, keep in mind, it doesn't matter if I have p plus q times p minus q, or if I have p minus q and p plus q. These actually don't matter. They're the same thing. This is basically saying 3 times 4 and 4 times 3. We get the same result either way. Okay? Example D. 16a squared minus 9. You guys are sharp here. Think about the square root of each of those terms. I'll pause. Difference, perfect square, plus minus, minus plus. So think, I'm going to pause about 5 more seconds. 5, 4, 3, 2, 1. Okay, so square root these numbers, you're going to get 4a minus 3 times 4a plus 3. So the signs are different, but your terms look the same. Your binomials. Okay, example number letter E. 25 t squared minus m squared. So we have 5t minus m times 5t plus m. Square root, one's a minus, one's a plus. That's the pattern for factoring the difference of two squares. Last example, f. 36x, minus 49x cubed. Now, I said this at the very beginning, we haven't really done it much today, but don't forget to factor your GCF first, if you've got one. See how these both have an x? Factor that out. So this becomes x parentheses minus 49x squared. Okay, factor that GCF out first. Difference, perfect square, perfect square. So this becomes x out front, 6 minus 7x times 6 plus 7x. That's the difference of two squares. Okay, so quick recap. Difference of two squares, you're going to have 1 minus 1 plus. You're going to square root each term, and that's what goes in your parentheses. Square root of 36, 6. Square root of 25, t squared, 5t. Square root of 9, 3. Square root of 16a squared, 4a. Square root of p squared, p. Square root of q squared, q. Difference, 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 difference. Don't forget, if possible, factor out your GCF. Okay? All right, you guys have been great. If I look at my notes, really we have about 12 more that we could do. This is kind of where we stop in class. I let you guys work on my math lab, let you guys answer questions. If you printed out the notes, there are more examples there. I just wanted to express my gratitude to you guys. Thanks for allowing me to do it this way. My hope and my goal is to be back on campus Wednesday. I stayed up in Tallahassee for a few more days to be with some family. My mother-in-law still is not doing well. And so I appreciate your prayers, and we're just praying for her right now as we walk this journey out. Thank you for your support. This is what I would have done Monday in class, so I actually taught it here. It's kind of worked out good. Thank you guys. If you have any questions, please let me know via email. Let me real quick close with this. I'm looking at our schedule and just kind of getting an idea, and I want to make sure you guys feel comfortable with this. Monday, Wednesday, Friday, Monday, Wednesday, Friday. This is what I was thinking. Today's video lesson is what we would have done Monday in class. Wednesday, we're looking at 11:6, I believe, which is a review lesson. Then we've got, I believe, 11:7. And if I recall, let me look and make sure I got my notes here. Okay, that would lead us with a test on chapter 11 right here. And this is SEU conference, which is the spiritual emphasis week that we talk about with chapels. So that actually works out good. We want to test before we get into SEU conference, because we really don't want us to test here the week of conference because you have late night chapels, and then that next Monday is President's Day. We don't even have school, or we don't have classes on those days. So if we don't test here Monday, February the 8th, it's going to be a drag before we get to that test. And the further we put it off, the more likely we're going to forget all this. This is a review lesson on Wednesday when I come back. Maybe just slightly some minor new things in 11:7, and then we can review a little bit on Monday right before the test if needed, and we'll do the test. My plan is to do the test on my math lab. That's kind of what we voted. If that does not work out, then we can change it later, do different styles in other chapters. But let's do my math lab for our test. It has to be done in the lab, in front of me, in the computer lab right there. Put a time limit on it of 1 hour, and it'll shut off right around 1 o'clock for us. Okay? Thank you guys for your appreciation, and I look forward to being back on campus Wednesday. God bless.